Hello, everyone. Let's get started with today's lesson on electron configurations, lesson 13 in your study guide. So get that out and let's get started. All right, so what we're going to do with this lesson is we're going to be applying the principles of the electron cloud model, the quantum model, or the wave mechanical model. In other words, our current model of the atom. And what we're going to do is learn a new way to organize or structure the electrons in the atom based on what we've learned about orbitals and quantum theory in general. Okay, so the way we do so is we use what is called electron configurations, and so yeah, let's go ahead and dive right into this, shall we? So to begin with, we need to talk about valence electrons, and it's pretty easy to understand. The valence electrons are electrons that are found in the outermost electron shell. Okay, so looking at this model of the atom, the Bohr model here, the electrons here in the outermost shell are known as the valence electrons. Okay, therefore, they're also found in the valence shell. Valence electrons, valence shell is the outermost shell. Now, the reason why we're going to distinguish them as valence electrons is because they are going to be the most important electrons in the atom concerning the properties of the element, as well as how it's going to interact and react with other things. So we need to have a clear picture of not only what an valence electron is, but how can we determine the number of valence electrons for any given atom. And we need to do so quickly, okay? Now, if you look at this particular model, this looks like this is a carbon atom. And we know that carbon has 6 protons, and we also know that it has 6 electrons because it's neutral, okay? So it has 2 electrons in the first shell, and then it has the 1, 2, 3, 4 electrons in the valence shell or the outer shell. And so we would say that carbon has 4 valence electrons, okay? But we need to get that number much faster than sitting here drawing out the Bohr model and trying to figure out, okay, it has this many in this shell and this many in this shell. We need to know it right away, okay? So I'm going to teach you how to do that, how to determine the valence electron number for any element very quickly, okay? And we can do so by using the periodic table. By the way, before we go on to that, the electrons that are not valence electrons are known as core electrons or the inner electrons, okay? Core inner electrons. And we will discuss the core and inner electrons from time to time and how they affect the atom, but mainly we're going to focus on the valence electrons in the outermost shell. Okay, so without further delay, this is how we're going to predict the valence electrons for an atom. Now, we got a blank periodic table here, and what I'm going to do is put in the period or the group numbers. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and finally 18, okay? Now, group numbers. Now, we know that the middle of the table here from groups 3 on over to group 12, right? This middle block, that's the transition elements, Okay, we call it TE, transition elements, or even trans elements, okay, in the middle. And so we're not going to focus on the transition elements right now. We'll briefly mention them, but we're going to focus mainly on groups 1, 2, 13, 14, 15, 16, 17, 18. Those are known as the main group elements, okay? Now, we can determine the valence electrons for the main group elements by looking at the group number, okay? And really the last digit in the group number. So for group 1, because it has only the last digit is 1, this indicates that there is one valence electron for every element in this group, okay? The group 2 elements all have 2 valence electrons. All of these 2 valence electrons based on the group number. Group 13 is going to have 3 valence electrons. Okay, the last digit is a 3, therefore it's going to have 3 valence electrons. Group 14 has 4 valence electrons. Group 15 has 5 valence electrons. 16 has 6 valence electrons. 17 has 7 valence electrons. And group 18 has 8 valence electrons, with one exception, and that is helium will only have 2 valence electrons. Be for valence electrons, okay? So we can quickly predict the valence electron number for the main group elements based on the last digit in the group number. So again, 1, 2, 3, 4, 5, 6, 7, 8, and then helium is going to be 2 valence electrons, okay? That's the only exception there in group 18, all right? So that number, again, I cannot stress the importance of knowing how to predict the number of valence electrons. For instance, let's say we have, this is boron, this is carbon, this is nitrogen, oxygen, fluorine, and then neon, okay? So let's predict the number of valence electrons. For boron, it's going to be 3. For carbon, it would be 4. For nitrogen, it'd be 15. Oxygen is 16 valence, or sorry, 6 valence. Let's go back. Boron is 3 valence electrons. Carbon is 4 valence electrons. Nitrogen is 5 valence electrons. Oxygen is 6 valence electrons. And fluorine is 7 valence electrons. And then neon is 8 valence electrons. So everything here, these are the noble gases, right? All of those noble gases are going to have 8 valence electrons, Be, valence electrons, with the exception of helium, which will only have 2. All of the halogens, all the way down, will have 7 valence electrons and so forth. So it just carries on right down the group number. All right, what about the transition elements? Well, their valence electron number can transition a little bit. All right, that's why one of the reasons why they're called transition elements. But for the most part right now, we're going to assume that they all have 2 valence electrons in their outer shell, as you'll see as we go through this. Okay, and that's pretty much true in most cases. Okay, 2. All right, let's move on. All right, now, have you ever wondered, we've talked about the shape, or like how the periodic table is structured into periods and groups. And we know that within a period in a group, we have these blocks, right? And each block represents an element, okay? And as I mentioned, the periodic table kind of, to me, looks like a castle wall, essentially. And the wall is made up of those brick blocks, which are the elements. And we've talked about that the structure of matter, the building blocks are the elements. Well, the building blocks of this castle wall are also the elements, okay? But it's weird shape design, okay? We got hydrogen that's clear over here in group 1, and then in group 18, we got helium. We got this big gap in between. And we know, I think we understand that helium fits better here in group 18 with the other elements in group 18, the noble gases, because they have similar chemical properties. Just like hydrogen fits better in group 1 because hydrogen has similar chemical properties as the other elements in group 1. And that's true for all elements that are grouped together. They have similar chemical properties, okay? But we do have some interesting spacing or gaps in the table. We have a specific structure. Well, that structure, the outline of the periodic table is really what we're focusing on, the outline, okay? The outline is based on the quantum structure of the atom, all right, in reality, okay? It's based on subatomic orbitals, the S, the P, the D, and the F subshells, essentially, okay? So the periodic table is really divided into what we call blocks, okay? We're not talking about the elemental blocks. We're talking about big blocks of elements, okay? So the first block of elements are known as the S block. And the S block covers group 1 and group 2, okay? And then the middle transition elements are known as the D block elements. And the groups essentially 13, 14, 15, 16, 17, and 18, those groups belong to the P block. And then these lanthanides and aconides are belonging to the F block, okay? Now, why do we divide them into S, D, P, and F blocks? Well, it has something to do with the S, D, P, and F subshells, okay? When we learned how to do electron structure earlier in the year, where we learned how to put the correct number of electrons into a shell. And we said, okay, in the first shell, we have 2 electrons. In the second shell, we can have 8 electrons, and so forth and so forth, okay? Now, we did that using the periodic table, and we pretended that each block of elements, so each element, that block, okay, is considered 1 electron, okay? And so we pretty much are doing the same thing here, but it tells you where that electron for that block fits into a subshell, okay? So for instance, we know that this first element here is hydrogen, right? This is hydrogen, right? And we know when we're building hydrogen, so it has 1 electron shell, and we know that hydrogen has 1 electron in the first electron shell, okay? But what subshell does that electron fit into? Well, the block of hydrogen right here, because it's in the S block, it tells us that this 1 electron is actually in an S subshell. And remember, we talked that we're going to represent a subshell by just using this dashed line. And then we're going to put an electron as an arrow in that subshell. What this means then is that hydrogen has 1 electron in an S subshell, okay? If you look at the next element, helium, right here, right? So that's helium, right? The electron structure for helium is actually 2 electrons, right, in that first shell. And so therefore, by the way, oh, I forgot to tell you. Ooh, I need to back up. Helium is actually, as it says S, it really fits right here. This is where helium should fit in our S block, okay? So helium can be in both places, all right? I forgot to mention that. That's a very important thing. So that means that the next electron for helium is actually in the helium has an electron in the S shell. And I'm going to put another arrow, and I'm going to put a down arrow. And I'll explain to you why it's a down arrow and not an up arrow later on, okay? So what we're saying is that for helium, we have 2 electrons in the first shell, but both of them are in an S subshell, okay? Let's do one more to kind of show you this. Let's do lithium, okay? So lithium is not lithium, let's do, sorry, boron right there. So boron's right there on the periodic table, right? So it has, for its electron structure, we got these 2 blocks, the hydrogen, and then the helium block, and then the lithium, and then beryllium, and then boron, okay? So when I was to draw the kind of electron shells here, I would put 2 electrons in the first shell, right? So 1, 2, and then 3 electrons in the third shell, right? 1, 2, and 3. So 3 electrons in the third shell. So this would be the electron structure for, but what about the subshell structure, okay? Well, what we're going to do is, because hydrogen and helium, these 2 blocks are essentially in what we know is the first energy level. We're going to put 1, and then we're going to put an S called the 1s. Now the 1 represents the energy shell, and the S is the subshell that an electron is in, okay? And there's our subshell, so the 1s. Now for hydrogen, we fit 1 electron in, the 1s, the first energy level, S subshell. And then for helium, we fit a second electron in, okay? And we know that we finished the first energy level with 2 electrons. So in the first energy level, there's only an S subshell. And then we go to the second period, right? We got to go all the way to boron, right? And there's 3 electrons in that second shell, okay? Well, what about the subshell? Well, because we're in the second energy level, we have the 2s, okay, is next, right? Here's the 2s, and it is a 1. So I'm actually gonna put our line. So we got lithium. So there's an electron for lithium's box, and then the next box is beryllium. So that's gonna have a electron, okay? So then there's this big gap, and we go to the p block. And that's because the next electron is going to go into the p subshell. So I need to draw a p subshell, and it's actually going to be the 2p, right? Because we're in the second period. So 2p, or second energy level, and I'm going to have a electron there, okay? Does that make sense? So the atoms are divided into S, D, P, and F blocks because they help us to put the electrons into the right subshells for an atom, as we're trying to work with the modern structure of the atom that we know of, okay? So we'll come back to this in more detail in just a moment, but it gives us a good start, I hope. All right, now before we go any further, we need to define some important principles or ideas when it comes to structuring atoms into subshells and energy levels in the quantum model, or the electron cloud model of the atom, okay? The first principle is known as the Aufbau principle, okay? The Aufbau principle, or the building up principle, okay? This basically tells us that we're going to put electrons in the lowest electron state, the lowest energy state possible, okay? So electrons like to build essentially going from the lower energy to a higher energy, okay? And that should make sense in a lot of ways, because we always start with the first energy level first, and then we go to the second, and then we go to the third and fourth and so forth. So in other words, we're adding electrons to the lowest energy state first, and then we keep on building up to a higher and higher energy level state, okay? So that's what the off-ball principle is trying to explain to us, is that we're always going to put electrons based on the lowest energy state possible, and that's going to be our guiding principle here, okay? And then once we do that, we're going to successively build electrons into different orbitals based on starting with low energy orbitals to high energy orbitals, okay? And so something will look like this, okay? So this is something you probably should write down so that you can kind of get this notation. So if we're looking at going by energy, so I'm going to put an arrow here, and this is going to represent an increase in energy. So again, we're going to start at the lowest energy state and then work our top to the top. So we are always going to start with energy level 1, right? The closest to the nucleus. And so we have our first principal energy level, that would be 1, right? Number 1. But what about the subshell? Well, there's only one subshell in energy level 1, and that's an S. So we're going to start out with putting electrons in the 1s. That's our first shell and first sublevel that we are going to fill. Once that's filled, then we're going to go to the 2s, the second energy level, and the 2s, okay? Now, we talked about in the last lesson that the P subshell is higher in energy than the S subshell. So in the second energy level, there is a P subshell, and it's going to be higher in energy. So I'm actually going to show that right here, and I'm going to put this as the 2P, okay? Now, what I really want you to understand is that the 2S and the 2P, they're both on the same energy level, okay? They're still in the second energy level. It's just that what we're indicating is that the P subshell is higher in energy than the S subshell, okay? Now remember that there are 3 different P orbitals, X, Y, and Z, okay? And I don't need to write them in any particular order, X, Y, and Z, all right? And sometimes I don't even write them. But just to indicate X, Y, and Z, those 3 orbitals mixed together, you know, combined together to form the P subshell, okay? Now, that's it in the second energy level. So the third energy level comes next. And what we have is an S subshell in the third energy level, so the 3s. And then we have a P subshell. So we call this the 3P, okay, which is higher in energy. So again, we're working our way from the lowest energy state up to the highest energy state. And so far, the 3P is our highest energy state. Now, next comes the D orbitals for the first time. And remember, there are 1, 2, 3, 4, 5 D orbitals, right? And that would be 3D, okay? But, a twist in the plot, you could say, okay? The next you would predict, the next shell is the 4th energy level. And we do have a 4s, but something weird occurs. Now, what's going to happen is, in reality, the 4s is actually going to be lower in energy than the 3D by a little bit. All right, by a little bit. And it varies a little bit from atom to atom. Sometimes the 4s is really close in energy than the 3D, and sometimes it's not. Okay, so it depends on the atom. But generally speaking, the 4s is actually lower in energy than the 3D. Now you're gonna ask, oh, why? Why is this? Okay, that doesn't make sense. The 4s is further away from the nucleus, right? Is it not? Yes, it is. The 4s is further away. It's in the 4th energy level. And the 3ds, well, the 3ds are in the 3rd energy level. So we would think just the opposite. We would think that the 4s is higher in energy than the 3d. So what's going on here? Well, the answer, my friends, is well more complicated than what our class is going to get into. Okay, I'm sorry to say. We don't have the time for it. It would take a lot of time. Sorry about the lights. It would take more time than what we really have for the year on this, okay? And there's a lot of scientists, chemists, physicists that are still trying to work out the details on this of why the 4s is lower in energy than the 3d in many different atoms. And the problem is that what we're finding is that the explanation to why is different for different atoms. So we can't just do a one-size-fit-all idea. We have to look at each individual atom, and based on those atoms, it's going to have a different explanation of why the 4s is lower than the 3d. So for this, for our class, you're just going to kind of have to accept this one, okay? Just chalk it up. You're going to accept that the 4s is lower in energy than the 3d, okay? The way it is, right? Now, I can tell you it has something to do with the balancing act between the repulsion forces between electrons and the attraction between the nucleus and the electrons, okay? So all of these repulsion and attraction forces in the atom are going to have a degree of a factor in this, okay? But that's as far as I'm going to get into it, okay? If you're more interested in it, do your own research, okay? So we're going to go building up the Aufbau principle. Then we're going to start putting electrons in the 1s, then the 2s, then the 3p, then the 3s, then the 3p, then the 4s, and then finally the 3d, okay? And then we go back to the 4p, okay? So then we do 4p. And then we keep on going from there, okay? The next is actually the 5s, okay? And then the 4ds, and then the 5ps, okay? So we keep on kind of rotating in that direction, okay? Now, again, this is the Aufbau principle. And what I still want you to understand is that the 4s is still an outer, it's still a shell further away from the nucleus, all right? It's still, the shells are in order. That hasn't changed. It's just that we're talking about energy here, not distance from the nucleus. We're talking about energy. And even though there seems to be a correlation for the most part, that as you're changing energy levels, you're also changing an increase in energy. But as you see with the 4s versus the 3D, that's not the case. There's an anomaly there, okay? Where even though the 4s is out here further than the 3D in distance-wise, the 3D is actually higher in energy than the 4s, okay? Try to make as much sense as you can, but that is really important idea to know, okay? So that's the Aufbau principle, and this is kind of our drawing. And again, what we're going to do is we're going to put electrons using arrows into these spaces here, and then until we fill them up, right? We're going to fill them up with electrons and so forth, starting at the lowest energy state, going to the highest energy state, okay? Hopefully that's clear. Okay, we're going to come back and use these boxes. They're a little bit, they're the same ideas using the dash line, but instead they're in a box form, okay? I think the dash line is much right. It's faster, so that's kind of what we're going to use overall, okay, when we get there. So we'll come back to doing this with atoms in a little bit. Okay, the next principle we need to talk about is called the Pauli exclusion principle. Okay, and what the Pauli exclusion principle says is that no atomic orbital can have more than 2 electrons. And we talked about that last lesson, is that each orbital only has a maximum of 2 electrons in it, okay? But here's something new. They must have opposite spin. What are you talking about? What we're talking about is the electrons have spin, okay? They spin in one direction or they spin in the other direction, okay? We're not going to get into the fine details of electron spin. That's, again, above our level in this class. It's way more complicated than what it seems. So essentially what we're going to do is just say that one electron in one orbital has one spin type and the other electron has the opposite spin type. So in order to fit in the same orbital, so let's say we have a 1s orbital, we must have one electron with one spin represented by the up arrow, and the down arrow represents the other spin, okay? So these two electrons have opposite spin, and so this is the correct way of writing it. You cannot have this. You cannot have 2 electrons in the same orbital space, with the same spin. You cannot have that. That does not work. That's in violation of the Pauli exclusion principle. So again, 2 electrons maximum, and they must have opposite spins. And we indicate that by the up and down arrow. All right, the last principle, the last principle is called Hund's rule, okay? Now, Hund's rule is, again, associated somewhat with the Aufbau principle, and that is that we're trying to put electrons in the lowest energy states possible, okay? Now, Hund's rule goes a little bit further with that. So let's say we have the 1s, and then we have the 2s, and then we have what? Our 2p, and there's 3 of them, right? 1, 2, and 3. Okay. Now, remember that the 1s has less energy than the 2s, and the 2s has less energy than the 2p. So with the Aufbau principle, we would start putting electrons here first, okay? And then we would fill this up with another electron with an opposite spin, Pauli exclusion principle, and we cannot put any more electrons in this orbital. It's impossible. So then we go to the 2s, and we have one electron with one spin, and we fill it up with an electron, another electron with the opposite spin. So we've filled up in increasing energy fashion. Ugh, jeez. Gosh, dang, sometimes, okay? So again, our energy should be increasing in this direction, E for energy, okay? Should be increasing, going up. So the next is the 2p, all right? So the next electron can go in any one of these p orbitals, and that's because all of these p orbitals have the same exact energy. That's why they're on the same level, okay? So I can put an electron here, or here, or here, okay? Well, the question is, where does the next electron go? Does it go here with an opposite spin and pair up? All right, that's one option. Or another option is that we put the electron in a different orbital with the same spin. Okay, so those are our 2 options. A, it goes in the same orbital with opposite spin, or in a different orbital with the same spin, okay? Which one do you think? Well, if you leave it at this, you would be correct, okay? And this is Hund's rule. Essentially, Hund's rule says it's a lower energy state if we put electrons with the same spin in different orbitals that have the same energy, okay? And that is, remember that when we put electrons in the same orbital, they're both negatively charged. And so there's going to be some repulsion here, okay? There is some repulsion that are going on here. But because they have opposite spins, they tolerate one another, essentially, okay? If they had the same spin, they would not tolerate each other, and they would push away too much, okay? Negative, negative, do not like. But the toleration comes in that they have opposite spin, and they can somewhat tolerate. But still, it's better if we can spread out the negative charge. So the next electron that we're going to add is right here. So where do you think the third electron would be? It would actually go into the next p orbital, okay? Now we have all the p orbitals half filled. And once they're half filled, then we go back and start filling them up with electrons with opposite spin, like so forth, okay? And that's essentially Hund's rule in a nutshell, okay? All right, so now let's get into actually building atoms using these principles that we've just learned, okay? So again, we're gonna divide the periodic table, the S block, and we're actually gonna throw helium over here, right? So this is our S block. This is the D block. Oops. It's gonna make capitals, really lowercase d. This is the D block. This is the P block, and this is the F block, okay? And I'm not going to spend a whole lot of time on F orbitals right now, but I do want to look at the S, D, and P specifically right now, okay? Now, we're going to use this periodic table to help us to kind of work out the structure of atoms. So we're going to kind of go back and forth a little bit, okay? But keep in mind those blocks, all right? All right, so what we're going to do is, let's say we want to draw the correct electron structure using shells and subshells and a diagram like this. Now, this is called an orbital diagram, actually, that we have been using, okay? So let's say, and I'm just going to throw a real quick example. You don't have to write this down in your notes yet. We'll do some other examples in just a moment. So let's say we want to do hydrogen, okay? I'm going to do a few examples to get us started, and then we're going to record some stuff in your notes, okay? So hydrogen, if you look at the periodic table of where hydrogen is, you know it's, oops, sorry, back. It is right here, right, on the periodic table. So it has one electron, okay? And since it's in the first energy shell, there's one electron in the first energy shell, right? And you know that, okay? So let's go forward a little bit. You might want to have a periodic table out right now. It might be handy to have one. Okay, so if I was to draw energy level 1, okay, this is N equals 1, I would expect to have 1 electron, okay, in energy level 1 for hydrogen, okay? So where does that fit in to our scheme here? Well, we're going to follow the Aufbau principle, and we're going to put 1 electron in the lowest energy state, which is the 1s, okay? So essentially, then, that the first electron for hydrogen, and the only electron for hydrogen, is going to be in the first energy shell, which is indicated by our, what we normally know as electron structure, plus the electron is going to place in the S subshell, okay? Now, I'm going to clear this, and I'm going to go to what we call electron configuration notation, okay? This is a faster way to do this than writing all of these orbital diagrams out, okay? So an electron configuration looks like this. It's a shorthand way of putting the electrons in the right energy levels and in the right sublevels. So for hydrogen, it has an electron configuration of what we call 1s1, okay? So again, the 1 represents the energy level, the S is the orbital type or the subshell, and then a superscript 1 represents the electron in that shell. Okay, so we just simply would write for hydrogen, its electron configuration is 1s1. Okay, and that's it. And that's its only electron configuration. And we actually call this its ground level. Remember, the ground level is basically the electron in the lowest energy state. Okay, so this is the ground level or lowest energy state electron configuration for hydrogen. Okay, now let's go back to some other examples really quick and see if you can start catching on to what we're doing here. Okay, let's say we're going to do lithium. So lithium, symbol Li, has 3 electrons total, okay? So we got to place these 3 electrons in our orbital diagram, okay? And we got to start with we got to start with Aufbau principle and Pauli exclusion principle and consider Hund's principle as well. So the first electron is going to go in the 1s. The second electron is going to go into the 1s as well, but with an opposite spin following the Pauli exclusion principle. And we can only have 2 electrons in there based on the Pauli exclusion principle with opposite spins. By the way, the electron structure would be something like this: 2 electrons in the first shell for lithium, and then the next shell you have 1 electron, right? And that's what we've learned before: first shell, second shell, okay? So the 1s, or the first shell, is filled with those 2 electrons. And then we're going to go to the next lowest energy state, which is the 2s, and we put an up arrow there, okay? And that's it. There's only 3 electrons. So this is the orbital diagram for lithium. This is the electron structure for lithium. But what about the electron configuration for lithium? Well, we know that we have a 1s orbital, and we have 2 electrons, so we're going to put a 2 up here as 1s2. And then we're going to go to 2s1. And this right here, my friends, is the electron configuration of lithium. 1s2, 2s1. Okay, that is as simple as it gets for the ground state of lithium. Okay, makes sense a little bit, hopefully. Okay, all right, let's clear this. Now, let's go to some let's go back. We're not going to go there yet. All right, let's go. I think in your notes, you have a structure that looks like this for carbon, okay? We're going to do carbon, okay? So this, you can start filling this into your notes down. We'll start with carbon. So we're going to draw the structure for carbon. So over here, how many electrons does carbon have? Well, carbon has 6 electrons, right? And so let's do the shell diagram. 1, 2. So it has first shell, second shell, and that's all it has is 2 shells. And the first shell has 2 electrons, and then you have 4 electrons in the second shell. Okay, so let's start filling this in based on our diagram here. So we're going to have 1 electron, 2 electrons. That's for the first electron shell. And then we're going to fill up an electron in the 2s, and then another electron in the 2s. And we filled that up, but we still have how many more electrons? Okay, well, we still have 2 more. Okay, and the next lowest energy state is the 2p. So we got to put those 2 electrons in the 2p now. All right, And so 1 goes in one of the p orbitals. And then we're going to follow Hund's rule here for the first time. And we're going to put another electron with the same spin in a different orbital. And so this is the electron structure really for carbon, all right, which has an electron configuration of 1s2, 2s2, and then 2p2, okay? I can do better with that 2 right here. Okay, so that should be a 2. So 1s2, 2s2, 2p2, okay? So that, again, is the electron configuration, or the simplified version of this orbital diagram. Now, what are the valence electrons? Well, we know the valence electrons are here in the outer shell. There are 4 valence electrons for carbon, and that is also indicated by this diagram here. There are 4, 1, 2, 3, 4 valence electrons, and right here, the 4 valence electrons, okay? Yes, the 2s and the 2p, they're both on the second energy level. This is the outer shell, or the valence shell, and there are a total of 4 electrons there, even though they're in different subshells, okay? The electrons are in different subshells. The outer shell is still the second level, okay? So keep that in mind, okay? Let's do another one. Nitrogen is next, okay? Well, how many electrons does nitrogen have? 7, right? So nitrogen has, in the first shell, 2. In the second shell, it's going to have 5, right? Yeah, 5 electrons, okay? So again, we start off with the lowest energy state, 1, 2, and then we go to the second level, and we put an electron there, an electron there. We need 5 in the outermost shell, right? This is the valence shell. So we got 1, 2, and then 3. We're going to follow Hund's rule, 4, and one more Hund's rule, 5. And there's our 5 valence electrons right here in the valence shell. Okay, 1, 2, 3, 4, 5. All right, following Hund's rule, following the Pauli exclusion rule, and following the Aufbau principle. We're doing well. Okay, electron configuration then is 1s2, 2s2, 2p3. Okay, and that's our electron configuration. Okay, good? Okay, good. Let's go to another one. What else is in your notes? Fluorine. Okay, so we're going to jump all the way to fluorine. Now, fluorine has what? Sorry, in the first shell, it has 2 electrons. And then in the second shell, it's going to have 7 electrons, right? All right. So we're going to fill in 1, 2, 3, 4, okay? And then we need to do 5, okay? So we have to have 7 total in the second shell, right? So that's 1, 2, 3, and then off our Hund's rule, there's 5. And now we can go back, opposite spin, 6, and then finally 7, okay? And so there we are, there's the valence shell for fluorine. Only one of the p orbitals is half filled. The other 2 are filled. And so total of 7 valence electrons. And the electron configuration should be 1s2, right? 2s2, and then finally 2p what? 5, 1, 2, 3, 4, 5, okay? 2p5. Okay, again, these are the valence electrons. I'm boxing them. The 5, 6, and 7, okay? Even though they're in different subshells, they're still in the same energy level. So energy level 2 is the valence shell, okay? Again, these are going to be the most important electrons in our final overall discussion. All right, hopefully we're starting to do this well. Okay, what's next? Neon. Okay, I'll do neon really quick. I think you can get neon. It's got 10 electrons, so you're going to start with 1 electron, 2 electron, 3 electron, 4 electron, 5 electron, Hund's rule, right? 6, 7, 8, 9, and 10. Okay, so that's our 10 electrons, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So again, valence shell here. And what we can see is that the valence shell is full here for neon. We can't put any more electrons because the next shell up, or the lowest state of energy, is going to be the third energy shell, or the 3s, okay? So the electron configuration for neon then, okay, would be 1s2, 2s2, and then 2p6, okay? And again, oops, this is our valence shell. We have 8 electrons in that valence shell. And we can't put any more electrons. And you know that. When the second energy level, you can only fit 8 electrons in there. And so we can't put any more at all. We're stuck, okay, with that. And then we got to go to the next energy level, which is the 3s at that point, okay? All right, so what else? What other element is in your notes that we need to do? Okay, phosphorus and argon. Okay, oh, we got a whole bunch in there. I got lights off, okay. So let's do this. Let's see what you can come up with, okay? Do phosphorus and argon, okay? Do that, stop this video and do phosphorus and argon and see if you can do 2 things. See if you can do the correct orbital diagram, okay, with the right electrons and the right energy levels and subshells, and then see if you can do the electron configuration as well, okay? Stop. Okay, I've given you some time. Let's do phosphorus, okay? So phosphorus should essentially have an electron here and here. It should have an electron, 2 electrons in the 2s. Should have electrons that are completely fill up the 2p. And then the 2s should be filled with up and down arrows. And then the 3p should have essentially 3 arrows that are in the same orientation, okay, same spin, but in different orbitals based on Hund's rule. And there's phosphorus, so it should be 1s2, 2s2, 2p6, 3s2, and then 3p3, okay? Now, what's our valence shell? Well, it's the third energy level, right? Boom. Third energy level, 5 electrons, which is 1, 2, 3, 4, 5. And we should be able to predict that on the periodic table because phosphorus is in group 15, and therefore it has 5 valence electrons, which is what we should see here, okay? So there's phosphorus. Argon, okay, so again, argon, we should have that full second shell with all the orbitals should also be full, like so. Okay, this should be full, and the 3p should also be full, okay? And then again, here's our valence shell, the third shell, and it should have 8 electrons in it, like all noble gases. Argon is a noble gas. Argon should have 8 valence electrons, which it does, 1, 2, 3, 4, 5, 6, 7, 8. electron configuration, 1s2, 2s2, 2p6, and then 3s2, and then 3p6, okay? And again, this is our valence shell there with our 8 electrons, okay? So there's the electron configuration, and here is the orbital diagram, essentially, that we need to look at, okay? So now what I want you to do is the next atom is calcium, okay? So I want you to do calcium on your own. So see if you can come up with calcium, okay? And pause this video, and then we'll come back in just a second and see what you came up with, okay? All right, I'm back, and you should be done with calcium. I had to change locations. My battery on my computer was dying, so I had to charge it, okay? But I am back. All right, so we were doing calcium, right? So let's do that. So calcium has how many electrons total? Well, if I look at my periodic table, I have 20 electrons for calcium, right? So calcium, then we're going to start out with, let's do actually, look at the calcium's electron shells. It's going to have how many? 4. So 1, 2, 3, and 4. So 2 electrons, right? And then it's going to have 8 electrons. And then it should have another 8 electrons. And then it should have 2 electrons, okay? So that's the electron structure. So let's see, as far as go here, we should have up arrow, down arrow. Our orbital diagram here, following Hund's rule, right? Okay, now you see how the bigger the atom we get, the more this we have to do. It kind of gets tedious a little bit, right? And then the 3s, and then the 3p, down arrows, okay? And then notice what happens. Instead of going to the 3D, right, we said that the 4s is lower in energy than the 3D, right? And so we're going to actually put electrons in the 4s before the 3D, okay? Just like our electron structure predicts, okay, that we should have 2 electrons in the fourth energy level, in this case the 4s, okay? Wow, so our diagram fits in, and our understanding fits really nice with the organization of the periodic table, okay? Now the electron configuration for calcium would be 1s2, 2s2, let's see, 2p6, 3s2, 3p6, and then finally 4s2, okay? Now, it's a little easier to write the electron configuration because you don't have to put this whole, all these arrows and so forth. It's just simpler to write the electron configuration. So usually that's what I'm going to have you do, is use the electron configuration instead of the orbital diagram, okay? I do want to note that the valence electrons is the 4s 2, as you can see in our electron configuration where it should be, right? And then all of these other electrons are the core electrons, okay? Energy shell 1, 2, and 3, okay? Boy, I know this is a lot that I'm throwing out at you, but it's so important. Okay, so the next one we're gonna do is titanium, okay? Now, this is where we're gonna start understanding why when we did electron structures, you know, putting electrons in the right energy levels, why when we got to the transition elements that we went one shell back, okay? So I want to note, okay, if we go and look at our periodic table where titanium is, right? Titanium is right here on the periodic table, right in the transition block, okay? So let's use this periodic table real quick and write the electron structure for titanium first, okay? So we have 1, 2, 3, 4 energy levels for titanium. 1, 2, 3, and 4, okay? 1, 2, 3, and 4, okay? So we have 1, 2 electrons, right? 2 electrons in the first shell. In the second shell, 1, 2, 3, 4, 5, 6, 7, 8, okay, electrons. In the third shell, we have 1, 2, 3, 4, 5, 6, 7, 8, okay, so 8 electrons in that third shell. And then in the fourth shell, we go 1, 2, that's 1 for potassium, 1 for calcium, 2 electrons, okay? Then we hit our first transition element, scandium. And what do we know? Well, we go back one level, right? So with scandium and then titanium, we're going to add 2 electrons back to the third shell. So really, I need to have 10 electrons in the third shell, okay? So that's the electron structure for titanium, because in the transition elements we go one shell back, if you recall and remember that, and that's important, okay? So let's go back to our titanium, okay? And see if we can draw the orbital diagram for it. Remember, this is our deal, our shell model, okay? So in the first electron shell, we have 2 electrons. In the second shell, in the S subshell, 2 electrons. And then we have this, and this, okay? And then the 3s, we're filling up. Going to the 3p, we're filling up. And then we go to the 4s, right? And we fill that up. Uh-oh, we still have 2 more electrons to go. Where do we put those 2 electrons? Back to the third shell and into the D subshell now. Wow, okay? That's why we have learned that when we get to the transition block, we get to that D block, right? The transition elements are in the D block. Now we start filling electrons in the D subshell. And it's going to be in the third D because the 4s is lower in energy than the 3D. So things start making sense. And we're going to follow Hund's rule here, where we're going to put 1 electron in one D orbital and another electron in the other D orbital, okay, following Hund's rule. And so this is essentially titanium, okay? So titanium's electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d2. Okay, So this is written in order of increasing energy, right? So our 3D is out there. Now, does that mean that the 3D is our valence electrons? No, the valence electrons is the 4s, okay? This is our valence electrons. Even though the 4s has less energy than the 3D is still on the third energy shell. So it is a core shell, okay? These two electrons in the 3D are in the core part of the atom, not the valence shell. So for titanium, the valence electrons are 2 in the 4 shell, or in the 4s. All right? So don't forget that. That's important. Even though we're putting electrons in the third shell at the end, in the 3Ds, it's still, those are not outer electrons, those are core electrons. Okay? Sorry. So think about it in that terms, okay? We're almost there. Let's do, the next one is iron. See if you can do iron on your own, and then I'll do it with you, and then do bromine. Okay, so pause this for a moment, and then I'll then turn it back on and we'll go through it together. Okay, so pause it right now. All right, you should have time to do iron and bromine. So let's do iron first, okay? So where iron is on the periodic table, remember, let's go back. It's sitting here in the transition block, right? Iron is a transition element. So it needs to have electrons that are going to be 2 in the first shell, right? It's going to have 8 in that second shell. And then we're going to go another 8 electrons in the third shell. And then it should have 2 electrons in the fourth shell. But then we're going to go back to the third shell, right, with scandium. And we're going to add 1, 2, 3, 4, 5, 6 more electrons here. So that's what? 8 plus 6 is what? 8, 9, 10, 11, 12, 13, 14, 15, right? 16, wait a minute. What is it? I got lost. 1, 2, 3, 4, 5, 6. Sorry. So 8 plus 6 is what? So 8, 9, 10, 11, 12, 13, 14, right? 14 electrons. Ooh. Okay. So I'm going to erase that and put in 14 electrons here. So we should have 14 electrons in the third shell. All right, let's go back to our diagram then. And start filling this in. So we have 1 electron, we have 2 electrons, we have 3 electrons, or 8 electrons we're going to fill in here. So there's our 8 so there's our 2 electrons in the first shell, 8 electrons in the second shell. And then we go to the 3s, 3p. Hopefully yours looks very similar to mine. And then we go to the 4s. Those are the 2 electrons in the valence shell. And then we're back to the 3D, and we should have 1, 2, doing Hans rule, 3, right? How many more? I forgot. 6 more? 1, 2, 3, 4, 5, 6, right? So that's 1, 2, 3, 4, 5. So, and then we go back 6, okay? So that should be what, 14 electrons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 electrons in the third shell, okay? Now, still our fourth energy level, our 4s, is the valence shell, okay? So don't forget that. So for our electron configuration for iron, should be 1s2, 2s2, 2p6, 3s, 2, 3p, 6, 4s, 2, and 3d6, okay? With this being our outer electron shell, okay? Good, there's the electron configuration and orbital diagram for iron, okay? So now let's do bromine, okay? So bromine has how many electrons? Well, if I look at the periodic table, it has 35. Holy crap, 35. Okay, so here we go. We're gonna start filling in. First shell, okay, that's 2, that's 4, going down, okay, so that's 8 plus 2, okay, right, 8, 10, 11, and then 12, 13, okay, so that's what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, okay, and then 19, okay, and then we go to the D block, okay, and those go all the way to zinc, okay, so that should actually fill up. That should fill up the D block, or the 3 Ds, and then we should have another some more electrons in the 4p, and that's it. That's what it should look like, okay, in the end of the day. So everything here should be filled except for this 1p orbital should be half filled in the 4p. So the electron configuration is so much easier to write. It's just going to be 1s2, okay, 2s2, 2p6, 3s2, okay, and then 3p6, 4s2, 3d10, 4s2, or sorry, that should be p, sorry, 4p 5, okay? And that's the electron configuration for boron, much easier to do, all right? Wow, there we go. Oh my goodness, this is a lot to take in, okay? So we've learned how to do orbital diagrams, we've learned how to do electron configurations for these various elements and atoms, okay? So I know we're not, you're not completely done with your notes. We have this in your notes still to fill out, okay? So what we're gonna do is these basically are for the electron configurations for these elements, okay? And so what we're gonna do is we're gonna stop the video here, and then we're gonna do a second video that will cover this section of this lesson, okay? So we'll end here, go back and review your notes before we actually do this, and see if this will make sense, okay? So that's it for right now. Make sure, again, you watch the second video on this, okay? And there we go.